Okay, imagine this. A big storm hits, power grid goes down, but your local microgrid, it keeps the hospital running, the shelter's lit, everything's fine there.
Hmm.
But then the main grid comes back. How does that little microgrid, link back up? Seamlessly, automatically, especially if, say, communication lines are still out.
That's the big challenge.
Right. And that's what we're diving into today. We're looking at this really cutting-edge study. It's got an autonomous fix for inverters.
Yeah.
They're the heart of these microgrids.
Absolutely. The brains and the muscle.
To manage power and reconnect to the main grid, all without talking anything. That's our mission.
Yeah.
Unpack this.
Yeah, it's a really significant paper. It gets into a new kind of control setup for these grid interactive inverters.
Yeah.
You know, the ones you absolutely need for bringing in distributed energy, like solar panels or local wind.
Okay.
Without these smart inverters, resilient microgrids just aren't happening.
That makes sense. So context is key here. Let's maybe break down the two main jobs these inverters do. First, there's the grid following mode, GFL.
That's right, GFL. Think of it as a follower. It sees the main grid, it syncs up, and it pushes power into it, following the grid's lead on voltage and frequency.
Got it. Follower mode. And the other?
The other is grid forming mode, or GFM. Now it's the leader. If the main grid goes down, the GFM inverter creates the grid for the local island, setting the voltage and frequency itself.
Ah, okay. So it can follow the big grid, or it can be the grid for its little island.
Precisely.
But yeah, the tricky part must be switching between them, and especially that reconnection part you mentioned. If a comms lines are physically cut in a storm, how does it even know the main grid is stable and ready? That seems like a huge vulnerability.
It absolutely is. That's often the weak link. How does the inverter get the message, grid's back, okay to reconnect? This paper offers a really elegant physics-based answer. No message needed.
Okay, I'm intrigued. So how does this clever solution actually work? They call it a direct control method, using something like control sync.
Yeah, control sync. The idea is pretty neat. You essentially have both control strategies, the GFL and the GFM, running in parallel inside the inverter all the time. They're constantly synchronizing in the background.
So it's like having two pilots ready, and they can swap controls instantly without, jolting the plane.
Exactly. It makes the switch between modes really smooth, no power blips or anything, very stable. But the really clever bit is detecting when to reconnect without communication.
Right, the detection. How?
Okay, so there's this thing called a synchro-check relay. It's basically an automated switch making sure voltage and frequency match perfectly before connecting two grids.
Standard procedure.
Right. After that relay closes, the inverter, still in its grid-forming mode, starts to actively probe, you could say. It watches two specific things very closely.
What it looking for?
It monitors its own active power output, how much power it's pushing out, and the system frequency.
Okay.
And here's the signal. If its active power injection keeps going up, steadily increasing.
Like it's pushing more power out.
Exactly. And at the same time, the system frequency stays rock solid, absolutely constant.
Because the main grid is so massive, right?
Yeah.
It won't budge.
Precisely. That's what they call the stiff grid effect. The main utility grid is so huge, so stiff, that this little bit of extra power from the microgrid doesn't change its frequency one bit.
So if power output rises, but frequency doesn't change.
Bingo. The inverter concludes, the stiff grid must be back online. It detects it autonomously, just based on that physical response. No phone call, no data link needed.
Wow. That's actually quite elegant, just listening to the physics.
It really is.
So what's the bottom line here? What does this mean for us, for the power system?
Well, it means microgrids can reconnect reliably even if communication fails.
Which happens all the time in disasters.
Exactly. It removes a huge dependency. They proved it works, too, with real hardware, real inverters, and a grid simulator. It significantly boosts resilience. Your local power island can rejoin the main grid safely, all on its own.
That's a major step up for microgrid autonomy, making the grid smarter, tougher.
It is, and knowledge like this is great, but applying it is where the value is. This kind of breakthrough really strengthens the grid, makes it more adaptable. It paves the way for, more self-sufficient energy systems, especially as we get more renewables dotted around everywhere.
It really makes you think, doesn't it? If our power systems can start listening for these subtle physical cues, these sort of invisible signals in the grid itself, what other complex systems could become more autonomous, more reliable, by learning to listen in similar ways?
Yeah.
Something to chew on.